Hey everybody, I'm going to talk about the properties of water, and I'm going to begin by just doing a quick review of the pH scale and how it relates to water. So when we look at the pH scale, we can see it's from 0 to 14. It is measuring from the acidic range down at the low numbers all the way up to what's called alkaline or basic on the high numbers. Right in the middle is what we call neutral, and that's at a pH of 7, which would be pure water. I'm going to show you why that is. So if we take a look here, what I've done is I'm representing what being acidic or being alkaline or basic actually means. Now, when we look at a molecule of water, we have two hydrogens and an oxygen, H2O as we know, and it's important to understand that those are three different elements that are bonded together. They're covalent bonds, generally pretty strong bonds. However, when we break those apart, we can see that we can break H2O into a single hydrogen, which is lost in an electron, and a single OH group or hydroxide group, which is gained an electron. And that helps us to then think about water as something that can be broken apart and what it means when we have different amounts of these H plus halves and the OH minus halves. And that's what acidic and alkalinity is all about. So looking down below, I've sort of just made this to represent what's happening across the scale, that when you get down to the very acidic end, what we're talking about is a solution that has a large number of these H plus ions, an ion being something which has an altered number of electrons. And these H plus ions are very, very reactive, right? Hydrogen wants to have two electrons on its first shell. It wants to be happy, as we keep talking about, and so it's very, very reactive. So as we get to concentrations of H plus that are very, very high, which would be like the battery acid level of acidity, we see very, very reactive. They want to grab on and to react with things, and that's the danger. That's why if you touch something that's very acidic, it can harm your skin. It can cause harm because it wants to react and bond with whatever it happens to come into contact with. On the opposite end, we see the same thing, just with the other half of the water molecule. We have these OH minus hydroxide ions over here, which are again very, very reactive. This oxygen and hydrogen, they want to have a full outside shell for both of the atoms, and so they will readily react with things. And that's like our hardcore cleaners, Drano and things like that. You know, if you have something like Drano in your home, don't touch it. Don't even look at it. It's super dangerous. But if you do look at the container, you'll see a million different warnings on it because it is so highly reactive, which is sort of the point of why we pour it down our drains, and it will clear anything that might be clogging it because it's just going to react away and eat away at whatever it happens to bump into. So all of that comes down to the fact that this water, we can view water as sort of these two different halves. Now, in the middle, where we have an equal number of H plus and OH minuses, well, those are just going to react together and just be sitting there as water. That's why water is the center of the pH scale. And that's also why we see when an acid and a base react together, we end up producing water as a product, because those OHs and the H pluses find each other and they recombine into water. So looking a little bit more at water, and we really stress this point that water is polar. Ultimately, all of the different characteristics and properties of water come down to the fact that water is a polar substance. And what that means is that even though water is one oxygen and two hydrogens, it is a total of 10 electrons and 10 protons if you count up two hydrogens and an oxygen. And that means that it's neutral. It doesn't have a charge. But the polarity actually means that the way that hydrogens share their electrons over towards the much larger oxygen creates a relationship where those electrons have sort of been stacked up on the oxygen side, which makes the oxygen side a little bit negative when compared to the opposite side of the hydrogens, which are therefore a little bit positive. So even though the whole thing is neutral, 10 electrons, 10 protons, it's not evenly distributed, those electrons. And so we have this slightly negative end and this slightly positive end. And that's ultimately the reason for every unique property that we see of water. For instance, when we look at cohesion, cohesion is the way in which water molecules stick together like a water droplet. You know, it doesn't just flatten out. gravity's pulling on those molecules. It should just flatten out, except those molecules are holding together for some reason. And the reason is because of the attraction between the positive end of one hydrogen on a water molecule and the negative end of a nearby water molecule's oxygen. Opposites attract, and so they hold together, and that creates this cohesive little, droplet, and is the reason why water kind of clings to itself. And we don't even think of that as being weird because we have such regular, interaction with water that it would be weird if it was any other way. But when we compare it to other substances that are not polar, they don't do that. They don't hold together in a big ball like that. You can make a pretty big droplet of water before it breaks and spills. Then thinking about adhesion, it's the same thing. The reason water adheres to things, you step out of the shower, for instance, and all the water on your body doesn't just fall off of you, right? That would make drying off so much easier. Instead, it clings to things, and like your hair might stay wet for hours after you take a shower, and that's because water will do this same positive negative attraction to nearby substances as well. And so that's what's happening there is the positive negative regions of the water are just sort of attracted to nearby surfaces and the positives and negatives on those surfaces. So again, cohesion and adhesion directly related to the polarity of water. We see the exact same thing with surface tension, and I included that same picture just to show you that here we have an insect. That's a pretty big, scary looking insect, and it's standing on top of the water. It's important to understand this is not floating. It's not in the water and the water's using this buoyant force. It's not like when we're sitting in a swimming pool or something, or on a tube or something. In that case, then, that's different. That's the water trying to fill the space that you're taking up, and that's a different kind of force. Here, what's happening is this stick bug, or whatever it is not even passing through the surface into the water, and the reason is because it's so light that the way it's pressing on the water isn't enough force to pull those water molecules apart. Because of that cohesion between water molecules, they just have this ever so slightly sort of sticky nature that they're holding together, and this bug doesn't weigh enough to push those apart. Of course, if you go try and walk on water, like we have enough weight that it just pushes the water apart, no problem. But things that are very, very light, like a paperclip or a leaf or a stick bug, they can actually sit on top of the water, again demonstrating this surface tension. Now, it's not until something else breaks that surface tension, which could be force, it could be an added something that we dissolve in the water or some chemical that could cause the water molecules to not be able to hold together, in which case then the poor bug would fall right into the water. Transpiration is a mechanism used by plants, right, to get their water from their roots all the way up to the highest leaves of the tree. You can imagine there's redwoods, hundreds of feet tall, that are able to pull water all the way from the ground all the way straight up. There's no big mechanical pump that's driving that water up. Instead, what's happening is it's this same sort of use of cohesion and adhesion of these water molecules sticking together, that as the water molecules are moving up the roots, they pull the next water molecule and the next water molecule and the next water molecule. So again, it's sort of an application of surface tension, cohesion, adhesion, but at the end of the day, it all comes down to the fact that water is polar. One additional one is that water is considered a universal solvent because of these positive and negative regions of water. If you take something like salt, which we saw salt as an example because the sodium gives away an electron to the chlorine, making the sodium positive, the chlorine's negative, they attract together. And they're both happy then in terms of the number of electrons they have on their outside level. But when you take salt and you mix it with water, as you probably know from life experience or understanding what oceans are, salt will readily dissolve. Those sodiums and chlorines will ditch each other, and the reason is because sodium's only held together to the chlorine because sodium's positive, chlorine's negative. But when you put it in water, water has all these negative and positive sides to it, and so they'll freely break apart and they dissolve because the negative ends of the oxygen are attracted to the positive sodium, the positive ends of the hydrogens are attracted to the negative chlorines, and so that's what that dissolving actually is. Those sodiums and chlorines are spreading out throughout the water, as you can see a little bit more closely here. So one last one to address, which is a little bit more complicated sounding, but it's, again, the product of the same thing, is this concept of high specific heat. And so water has this property that makes it very challenging to get it to boil. You know, as a famous saying, right, a watch pot never boils. It's the idea that you have to sit there and wait and wait and wait and wait. If you've ever tried to like make pasta or something, you know, it takes forever for water to boil. And the reason is because as you're adding heat to the water, those water molecules, what heat really translates to is kinetic motion. And so those water molecules start moving. And, you know, if there was no other forces, then as those water molecules are moving fast enough, they could peace out into the air and just evaporate, right? But with water, the reason why that's so hard to do is because as you start to move one of these water molecules, all the nearby ones are clinging onto it because of this polarity, because of this positive-negative interaction. And that's what's known as a hydrogen bond, this attraction between these water molecules. And those hydrogen bonds prevent water molecules from moving around too much, because if you move one, you got to move all the other ones that are attracted to it, and then you got to move all the ones that are attracted to that one. And so it's this slow process of adding heat, adding heat, adding heat. And so specific heat is a measurement that determines basically how much energy needs to be added to a substance in order to increase its temperature. And for water, because of its polarity, that's a very, very high value. So it has a high specific heat. It takes a lot of energy and a lot of time to increase the temperature of water. And just to give you a quick comparison, if you've ever touched like rubbing alcohol or maybe acetone, nail polish remover, that kind of thing, or even like if you've ever gotten gasoline on your hands, I don't know what you guys do in your free time, but you know, you've probably at some point had touched one of those substances or been around one of those substances and been aware of the fact that, you know, rubbing alcohol, for instance, or acetone, if it gets on your hand, it feels very cold and it's like gone quickly. It doesn't stick around. It's not lingering on your hand. And the reason why it feels so cold is actually because it's evaporating very quickly. It's taking the heat of your body and using that heat to increase the temperature of the molecules and cause them to evaporate. And it happens very, very easily. Just with like the temperature of your hand is able to provide enough energy to evaporate those. Now compare that to water, right? You can't just pour water in your hand and watch it boil away. Water takes tons and tons of energy. So things like rubbing alcohol have a very low specific heat, and we can use that as a comparison to understand just how significant the polarity of water is to creating a very high specific heat. So this has been sort of a quick overview of things that we've read about so far, and we're going to keep working with this. If you have questions, let me know.